And so now we're going to go on to looking at white dwarfs. So these are the cause of dying stars. And just to put them in perspective, here we have the size of the Earth. The white dwarf is approximately the size of the Earth. Actually, you'll see they have some interesting behavior. They get smaller the more massive they are. And there's just another picture of a white dwarf. Okay, so basically what you've got is you've made a carbon core. It is degenerate. It never ignites. And you've lost most of the mass from the outer part of the star because it's been pulsating and losing mass over the course of the AGB phase. And so now we're just left with that remnant core. And so for stars that are above about 1 solar mass but less than about 8, we get this carbon that's produced in the core from helium burning. You actually do get white dwarfs formed by having from lower mass stars, but in that case they never switch on the helium burning. The degeneracy stops them from ever switching on the helium burning, and so they are degenerate helium rather than degenerate carbon. Remember that white dwarfs are not burning fuel. They're simply very, very hot and taking their time cooling down. And so they're usually made of carbon. There'll be some oxygen in there, and they're about the size of the Earth. And like I said, the more massive they are, the smaller they get. So here's basically, remember that there was some material that was left that collapsed, and that's what caused them to heat up. So the very surface is normal gas, but the center is going to be mostly carbon. And we'll get on to the fact that you have some other things that can form too. And the degenerate electrons are moving very fast, but they can't slow down because then they would defy the Pauli Exclusion principle. But there are also nuclei in there. It's only the electrons that are degenerate. The protons and neutrons are not degenerate, and they can lose energy. And so what you get is that you'll get shining due to the loss of the radiation from those particles. And so you can think of these things as being dying stars losing what's left of their heat. Now, I would say this is an underestimate, but eventually they cool down. So they're always getting less bright. They're losing energy. They don't have any way to make energy, so the luminosity is going down. The color is also changing. So they go from being actually ultraviolet bright through visible, through yellow, red, into the infrared, and so on, until they'll be basically, they won't ever reach absolute zero, but they'll get asymptotically close to it. Actually, if you calculate the timescale for this, it's more like trillions of years. It depends on what the temperature of the star is to start with and its surface area, because that dictates how fast it can lose mass. So, we've already covered this when we talked about the helium flash, but remember that the Pauli Exclusion principle says that you can't have two identical Fermi particles in the same quantum cell. And remember that our quantum cell is basically both geometrical space and momentum space. And so what you get is that the difference in the space and the momentum cannot be less than the Planck's constant cubed. But you can have two in a space because you can have spin up and spin down. So here I'm kind of trying to demonstrate what this means in reality for being able to calculate the size of the cell and how compact they can be. So if we consider a geometrical volume of 1 meter cubed, and so now we've got rid of our deltas in space and we just have our momentum, and that has to equal h cubed. So now I've kind of drawn this as a phase space, so I've got a volume of 1 meter cubed, and within it you've got particles that can have momentum between p and p plus delta p. And so you have this momentum space in which they can exist in this delta p. And so we're going to have a number of quantum cells that can exist, which is NQ for quantum cells, between momentum p and momentum p plus delta p. And it's just the surface area of this quantum space, so it's 4 pi p squared times delta p, because this is a very small size, and so that's basically the size of this shell, and that has to be divided by the h cubed. It cannot be less than that. Okay, so that's what we just came up with. NQ equals 4 pi p squared delta p over h cubed. And so we can then put in the number of electrons between p and p plus delta p has to be less than 2nq 8 and so this is just then taking the area in between that you can actually fit these in. And so this is 2nq, which just makes this 2 times that. Okay, but now I'm putting this in, so the momentum of an electron is the mass of an electron times its speed, so we're putting this in as being the momentum in terms of speed. So we've got the mass of the electron mu. Okay, so that's the equation we just came up with. But remember that particles have a Maxwellian distribution under temperature. So for a given temperature, you can say that the distribution of energies is going to be given by this distribution here, where this is basically the energy of the electrons. And so it has to obey this according to the temperature, and it has to obey this according to the Pauli exclusion principle. So this is only true if it doesn't violate this. And so you can basically put these two together and get an equation for when do these fit, when do these work. And so this is basically plotting those two equations. Let me just back up a second. So I'm going to plot this one, which is the Maxwellian, and this one, which is the limit at which you run out of space to pack them in. So here I've got, this is the velocity of the electrons, and this is the energy. Electron density. And so what we have is that according to NE max for Pauli, it's up here. This is for a gas that has a temperature of 100,000 Kelvin and an electron number density of 1.5 times 10 to the 23 per centimeter cubed. Okay? And you can see here that the Maxwellian distribution does not go anywhere, it's close down here, but basically it's not crossing over the Pauli line, and so it's fine. In this case, you don't have any degeneracy. Everything is permitted, and so we're good. So for this temperature and electron density, we're safe. Everything is permitted by Pauli exclusion principle. However, what we're doing here is we're basically taking it still at the same temperature, but we've doubled the electron density. And so this is the original curve that we had. This is the electron density this is the electron density that we had back up. I'll come back to it. This is the new electron density. And you can see here that there's this portion here that violates the Pauli exclusion principle. You can't have electrons with these speeds and at this density, because they will be too close together for the number of permitted quantum states. And so what does that mean? Well, it means that we're going to have to give these electrons some energy so that they're up here instead. Okay? And so we can't have them here, but we can have them in the striped region. But if we increase the temperature, so now we still have this higher density, but now we've increased the temperature to 300,000, and again, we are no longer violating that principle. And it's because as you go up in temperature, you have more options of different speeds. And so this is why when we talked about the AGB phase, for the low mass stars, they generate less energy inside, so they have lower temperatures in the core, and so they become degenerate, whereas the higher mass stars don't become degenerate because although they have high densities, they also have higher temperatures, and so you don't actually violate the Pauli exclusion principle. But we have to actually take some energy from the protons and neutrons and give it to these electrons so that they're now moving at speeds up here. So instead of moving at speeds around 5 to 10 kilometers per second, they're now moving closer to 20 kilometers per second. So what does that mean? Well, remember that the speed of the electrons gives rise to a pressure. So we have a pressure due to the electron degeneracy. And that is what is counteracting gravity. And so we now have something that stops them from getting any closer together. So let's talk about this with respect to the helium flash again. We talked about this when we talked about red giants. But if we had a core that was made of ordinary gas, then the ignition would cause an expansion. But degeneracy pressure is not, it doesn't fit the ideal gas law, right? The expansion happens in an ideal gas, a regular gas, but not in a degenerate gas. So the core doesn't expand. But it means that the temperature increases and the rate of the triple alpha increases, so the temperature increases even more until eventually it becomes non-degenerate. When it becomes non-degenerate, then you get the core expands and cools because it uses some energy to expand, and that causes a restructuring of the entire star, and this is when we get to that yellow giant or yellow subgiant branch, and we get core helium burning. But we're really talking about white dwarfs, so this is where we're talking about how we've no longer got any nuclear fuel. It's contracting, it's radiating its thermal energy away until eventually it can't contract any further, and it has electron degeneracy. But the more massive the white dwarf, the smaller its radius. And this is because at higher temperatures you can squish, you have more options. Your Maxwellian is such that you have more momentum space. You have more options of velocities that your electrons can have, so you can get them closer together in space. And so what that means is that for a higher temperature, it gets smaller and smaller. And in fact, once you get to, and this is, there are some error bars on this number, but basically, for a star that's solar composition, the core that's left over, if that core is more than 1.4 solar masses, it will just disappear. In fact, it doesn't become degenerate. It's always hot enough, and it will go past having a carbon core, and it will produce the next level, which is actually an oxygen core. And we'll get onto that later. Now, like I say, at this point, you're reaching a point where you no longer have white dwarfs. I'll give you a qualification on that statement. But basically, this is called the Chandrasekhar limit. This is Chandrasekhar, not one of our professors. Chandrasekhar came up with this limit for the mass of white dwarfs. So what happens with cores that are more massive? Well, you can see here, this is a measure of how big they are in terms of solar radii. So this is about the radius of the Earth. If you've got one that's very small, it's bigger than the Earth. And then when you get down to the biggest ones, they're smaller than the Earth, till eventually they just disappear. But actually what happens is you don't see them as white dwarfs because the stars don't go through that AGB phase. Okay? Now, what happens above 1.4 solar masses? And remember, this is the core mass. So you can think of this as being, I need a core that is more, the core of the star is where you do the nuclear processes. It's not the mass of the whole star. It's the mass of the core. If you go back 30, 35 years and you look at TV shows on stars, they actually get this wrong because they understood this limit, but they didn't understand that stars lose mass during their evolution to this point. So you can actually find Carl Sagan getting this wrong in Cosmos. So, stars with cores in the mass range of 1.4 to 3 solar masses will become neutron stars. We'll get into the processes it goes through when we talk about high mass stars. And so why can we have, neutrons are also fermions. Why aren't they subject to the same Pauli exclusion principle? Well, they are, but because they're more massive, you also have more options of velocities. The low mass of the electron means that MV is much more limited in its number of velocities that you can have. And so you can achieve higher densities with the neutrons, but eventually you do hit that point, and that's where you get a neutron star. And so remember that if you have a star that is less than, an object that is less than 0.8 solar masses, it won't actually do fusion, and so you get a brown dwarf. This is actually wrong. I would put this at 0.8, not 0.25, but this is from a textbook again. And it actually depends on some other factors, which we can talk about. But you may not switch on the helium burning. You may get a degenerate helium core that never fuses, and then you get a helium white dwarf. And then you're going to get a carbon core, and you get a carbon white dwarf. Above about 8 solar masses, actually this is a kind of gray area that somewhere between about 8 and 12, you still don't go to having a neutron star. That when you burn carbon, you may make oxygen, and then you burn oxygen and you make magnesium, and then you burn magnesium and you get neon, and so on, which is beyond the scope of this course, but I can talk to you about it. And so what we get is, again, a stalling out of the process. The neon or the oxygen or the magnesium becomes degenerate, never fuses, and so you effectively go through the same thing again, that you now have stars that end up with whatever's left over in the core as the white dwarf. Above about 12 again, this is an approximate number, we still don't have good limits on this, we have a supernova, and that's where you get as far as having neutrons sticking together. So let's just look in detail at the neutrons before we finish with this topic. And here we have the maximum number of neutrons is nn. So it's basically the same equation where this is the number of neutrons within that cell, the number density of the neutrons within that cell, and we have now the mass of the neutron. But if we compare this to the neutrons for the protons, basically everything is the same except for the mass. And so what you get is it's proportional to the mass of the neutrons cubed versus the mass of the electrons cubed. Well, this is a factor of 1,000. So you have a much bigger momentum space that you can play with, and so you have many more options of velocities that are permittable, and so you can actually squish them closer together. And that's where we're going to stop with this topic, and we'll move on to talking about high mass stars very shortly.